Okay, so we'll move on to our last speaker of the morning, Hong Liu from MIT, who will tell us about emergent entropy.
Okay, good.
This is the big one. This one is forward. This one is back. The button don't press.
Okay.
This is the light.
Okay. 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 Yeah. Yeah. I also want to thank the organizers for the invitation, and it's a very great pleasure to be back to Tel Aviv again. Oh. Something is wrong. Which one? Oh, this one. Oh, okay. Okay. Okay, modern technology. Good. Yeah, so we all know the second law of thermodynamics. Oh, no. We all know the second law of thermodynamics, which says that, say, if you have a system and you in equilibrium, you perturb a little bit, and if the system evolves in a thermally isolated way, then the entropy always increases. And of course, this law has a long history, started from Carnot by studying the heat engine, and then many people developed in 19th century. Yeah, and this is also arguably one of the most widely applicable laws in nature, and from the, say, galaxy formation to atoms, to biology, etc., really governing all aspects of the universe. And at heuristic level, the second law also implies error of time, because the direction of the entropy increase points to the and who's this? Of course, in the real world, we do observe error of time, and the precise origin of the error of time from the fundamental laws, which are symmetric in time, has been debated for long time. So at the heuristic level, the second law said the system should become increasingly disordered, and which is often considered to be self-evident. And so most of the time, people just thought the second law is self-evident. But actually, the derivation of the second law from first principle is actually non-trivial. Actually, there are very few and far between. And actually, there's also no general derivation for any systems. And the current derivations are always for some special situations. For example, the most celebrated Boltzmann H theorem applies only to dilute gases. So despite this long history and the very widely applicable nature of the second law, it's fair to say we still don't have a full understanding how does the second law emerge from the fundamental laws in nature, and also what are the minimal inputs one should put in order to see how it comes how it comes out. So these foundational questions should not be worried about only by those people, say, who are interested in 19th century physics, but they actually also have some bearings in 21st century physics. For example, through holography, we know that, first we know that black hole also has a second law, and through holography, and we know that second law is actually related just to the standard thermodynamic second law. And more generally, we believe for isolated quantum system, the thermodynamics should be understood essentially come from the quantum entanglements. And in the light of the holography, and again, this points to that both quantum entanglement aspect and the thermodynamic aspect have non-trivial implications for the space-time. And so the second law really plays a key role for understanding, say, black holes, etc. And in fact, actually, for most microscopic systems we observe in nature, actually, including far from equivalent situations, there's actually additional second law, which is actually a local version of the second law. And so this goes as follows. So let's consider, so for the many real-life situations, the variation scale of physical quantities, for example, the density, say, of the material or the temperature variations, they're often much, much larger than the molecular scales, which defines your typical relaxation scale. So then at distant scales of order, say, d, which much larger than your relaxation scale, much smaller than the variation scale of physical quantities, then you can approximate the system, say, to be in the local equilibrium. Okay? And in particular, if you take a continuum approximation, then you can essentially take this relaxation scale goes to 0. And then you can say, actually, each point, each space-time point should have a local equilibrium. And so that actually implies, intuitively, at least intuitively, that you should be able to define entropy at each space-time point. And also, from the second law, that the entropy production at each space-time point should be non-negative. And indeed, when you try to formulate, when you try to describe the dissipative system, a crucial ingredient, phenomenological ingredient, is the so-called second law, a local second law of thermodynamics, which requires you introduce a local entropy current, and whose 0 component would be, say, the local entropy density, and then we require that this this entropy current should have a non-negative divergence, at least perturbatively, say, at the level of derivative expansion. And this is postulated, but this is only postulated, but it's undoubtedly correct, because without imposing this constraint, and say your description of the dissipative system will not agree with nature. Okay, so this really plays a key role. And so what mainly I want to talk about today is a recent result to have new proof of the second law in some situations. So so this is joint work with the Paulo Glorioso, who is now a postdoc at Chicago. And so the main input of our new proof is assumption of unitarity, and then a Z2 symmetry, which characterize, say, time reverse and local equilibrium. And then you can prove that actually then you can actually give a general proof of the second law for the local equilibrium systems. And so this is actually much more general, for example, than the dilute gases. The H theorem applies. So this will apply to general liquids, say, critical systems, and also quantum liquids such as superfluid, etc. And also, you can prove a local version of the second law perturbatively to orders in the derivative expansion. And also that gives you an explicit algorithm to construct this this entropy current, say, in the non-equilibrium situations, but it's, Okay, so now let me describe the input, these two inputs which we use to prove those statements. Before saying, before describing those inputs, let me just make a few general remarks. So first, that the second law exists only after cross-graining, because we do know that the fine-grained entropy, say, the volume entropy actually remains constant on the unitary time evolution. So there must be something you need to do in order to have the second law. And the second is that the cross-graining itself actually does not induce error of time. So error of time somehow has to come through something else. Okay, just by cross-graining itself does not give you that. And also that the second law operates at the classical level. in the thermodynamic limit. In general, we expect both statistical fluctuations, say, and the quantum fluctuations, and in principle can say can drive your entropy down. You don't have to be always to be say increase when you include those fluctuations. And so in order to prove the second law, then you should operate at classical level and then in the thermodynamic limit. And ironically, it turns out the best approach to this problem is actually to start with the general general quantum many-body system, and then you do the cross-graining, and then you go to classical limit, and then you go to thermodynamic limit. And one of the reasons is that the cross-graining in quantum system is much easier to do than in the classical system. And also, from here, we will see some interesting surprise that actually quantum unitarity plays a very important role for the second law. Yeah, so now let me describe the two main inputs of the discussion. So the first is the cross-graining. And cross-graining is done, let's imagine we start with a general quantum many-body system, say in some state, which I call those zero, which describe some macroscopic medium. So this is way above the vacuum, okay? And so since we are interested in the real-time dynamics, and in some state, and so you actually need to consider this doubled contour, this so-called closed time path or Schwinger-Kaddish contour, which Logan already mentioned earlier today. And so in this formulation, say if you're interested in expectation value in this state, then you do the path integral. Then you have two paths, and then that reflected. You have a doubled field, and then the action. And then you have action associated with each leg of the contour. Okay. And to do the cross-gradient, what we will do is we will integrate out all the fast modes. Okay. And so imagine you integrate all the fast modes in this path integral, then what remaining is the path integral of the slow modes, and then you have effective action for those slow modes. So now let me make a few comments on the slow modes. So at the heuristic level, the slow modes are essentially just long-lived gapless excitations. Okay. And slow modes can be considered in two types. So the first count is conserved quantities. So you can argue in the general medium, conserved quantities always give you slow modes. So this part is universal. Okay. And the slow modes associated with conserved quantities are essentially just hydrodynamic modes, and then the effective action for them essentially is just hydrodynamics. And yeah, in last year's string conference, I described how you can say build an action, say for hydrodynamics, using this closed time path formalism. And there's a lot of then a system can have other, say, slow modes, and that would be system specific. Say, for example, all the parameters near a critical point, or near a Fermi surface, or if your system, say, have Goldstone bosons, have symmetry breaking with Goldstone bosons, and then you will have, then you can have additional slow modes. Anyway, the details are not important. For us, we only need to know that we have some, you can integrate out those fast mode, and then you get the path integral for the slow mode. Oh, yeah, and of course, the underlying assumption is that there's always a separation of scale between the fast modes and the slow modes, which is actually present in essentially all systems in nature. Okay, so the basic picture is say we have some macroscopic description. We want to find we want to describe the macroscopic phenomenon, and then this effective action then can be considered as the Bayer theory defined as some UV cutoff, which separate your fast mode and the slow mode. Okay, And then given this Baer theory, and then you can get your low energy phenomena, say doing the standardization group and the universality, etc. And so this low energy effective action come from this real-time formulation contains the so this is real-time and includes the dissipation, retardation, and the fluctuation effect. Okay. So right now this formulation is generally quantum. So this applies to any quantum systems, but you can also take a classical limit. Okay, when you so the interesting thing is that when you take a classical limit, the path integral actually survives. It's because even when you go to the classical limit, there's also statistical fluctuations. And so if you carefully take the h bar goes to 0 limit, you find actually you don't go to the saddle point. And actually the whole path integral survives. And the saddle point of the path integral actually corresponding to the thermodynamic limit. And so if you are interested in the thermodynamic limit, then we look at the equation motion, say, of this effective action. Okay. Good. So come from this evolution of come from this doubled integral of a quantum system, and so this effective field theory action actually should satisfy constraints from the unitarity of the time evolution. Okay, from unitarity of the time evolution, and one can derive there are three such kind of constraints. So the first one is that if you take the complex conjugate of this effective action, and then you get the minus sign, and then you switch these two copies of your fields. Okay, and so this is the first one. And the second, so this implies actually the effective action must be actually complex. There will be imaginary terms. There must be imaginary terms which are, so this means that term is symmetric in the exchange 1 and 2. And it must be imaginary, because when you exchange one, term is symmetric in 1 and 2, then you just get a minus sign, and then this is imaginary. And the second constraint is that the imaginary part of this effective action should be greater than 0. And the third one is that if you take the two copies of dynamical variable to be the same, and then actually the whole effective action should be 0. Okay. So to have some intuition where these three constraints come from, let me give you a heuristic explanation. Okay. So when you integrate out the fast mode, you can imagine the integration procedure corresponding to integrate out the fast mode in the background of the slow mode. Okay, because slow mode is very slow. Essentially, they don't move. They provide the background for the fast mode. And so essentially, you can imagine this effective action corresponding to integrate out the fast modes now with unitary evolution with this slow modes as the background fields. Okay, and then the two copies then corresponding to two different now the two lags have the two evolution, because this chi1 and chi2 don't have to be the same. So now keep this picture in mind. And now if you take a complex conjugate, so essentially if you look at this evolution, you take a complex conjugate, then you just exchange 1 and 2. Okay, that essentially is this relation. And this relation essentially comes from, suppose you start with the initial state psi, and then you evolve with one unitary operator, and then you evolve back with another unitary operator, and then you take the overlap with original wave function, and this is always smaller than 1 due to the unitary nature of those matrices. And so this is the so-called fidelity. Okay. And the third one is that when you take the chi1 equal to chi2, and then when you take the trace, then of course this will be equal to 1. Okay. And so these are very simple constraints, but should be satisfied by the effective action. And I should emphasize such constraints purely reflect the real-time evolution, and they are not visible in the Euclidean, say, low-energy effective series. And also, those constraints actually survive in the classical limit because they are just a constraint on the action itself. When you take h bar goes to 0, and they actually survive. Okay, and so actually they impose non-trivial constraint even in the classical limit. So now, since we are interested in the local equilibrium systems, and now we also want to impose the condition of the local equilibrium. So the question is, how do you do that? So one can get a hint on just in the thermal state. Okay. So so if you consider the correlation functions in the thermal state, and they satisfy a set of constraints, say so-called the Kubo-Martin-Schwinger conditions. And the familiar example is that for the Euclidean two-point function, and this just means that the Euclidean two-point function should be periodic along the time circle. But now if you apply this KMS condition to this real-time path integral, and actually something rather non-trivial happens. It turns out when you apply this KMS to this counter integration, you don't get back to itself. What you get is you get the counter integration with the rho zero with the state defined at t equal to plus infinity instead at t equal to minus infinity. Okay? So now if you want to apply KMS to the effective action describing this path integral, does not map it to itself. They map to some other effective action describe this reversed process. Okay. So it actually does not provide any constraints on the effective action itself, and only map you to some other process. Okay, map it to some other process. But however, if the system is also, but now suppose the underlying system is also invariant, say under say certain discrete symmetries containing time reversal, and then now you can just apply a time reversal and then go back to your original setup. Okay. To your original setup, and so I want to emphasize both both this discrete symmetry and this KMS, they are D2 operations. And this also tells you if you want to impose something like a KMS or the time reversal on your effective action, you have to impose them together. You cannot impose them separately. Okay, it does not make sense to impose them separately, and that makes sense. An intuitive sense physically, because as I emphasized, the effective action here, they contain dissipative effect. At the macroscopic level, they contain dissipative effect. And so there's no, so it makes sense, there's no straightforward action of the time reversal. And turns out, but if you combine with KMS, and then there's a well-defined action. Okay? This is a key. So now, we conclude that the theta and the KMS have to be imposed together. So motivated on this, and then one can propose a D2 symmetry, okay, propose a symmetry, and then you require your effective action to satisfy this D2 symmetry. So this tilde, this chi1 tilde, chi2 tilde defines some kind of D2 operation on your original dynamic variables. Okay. And the precise form of this D2 transformation differ for different fields. So let me just give you an example. Suppose let's give you a simple example. So let's consider you have a scalar operator, a scalar order operator, say in the classical limit. And then let's take this the discrete symmetry to be the PT. Okay, for example, take PT. And then this D2 transformation have the following form in the classical limit, and you define the symmetric combination of them and anti-symmetric combination of them. And the symmetric combination, they just invariant, just changed by the space-time reflection. But the anti-symmetric part, they change by the space-time reflection, then plus such a piece which is corresponding to a shift, an infinitesimal shift in the local temperature. Okay, in the local temperature. And so this condition should be viewed as really define what we mean by the state which are in local equilibrium. Okay, a state in local equilibrium. And this specifies a class of states. And this class of line equilibrium state, of course, also includes the trivial case, which is the thermal ensemble itself. which motivated by this proposal. But this can also include a much larger set of states, including, for example, the pure states, for example, the black hole macro state. And so this is just a postulate, and then you can check. So, for example, when you apply it to the action of the hydrodynamics, and then you find that this precisely gives you what you wanted. Say, for example, this gives you the local first law, and this gives you the uncyclic relations, which should come from the time reversal. And this also gives you the local fluctuation dissipation relations. Okay, and so that's consistency check at this kind of D2 symmetry actually is what you want. Okay, so now with those inputs, now we can prove a theorem. Say for any action satisfies these three constraints follow from unitarity, and this D2 symmetry, which we call dynamical KMS symmetry. Okay, this is D2 symmetry, and then you can prove that there always there exists a current S mu, which satisfies that when you integrate the zeroth component of the S0 and say integrate over all space, and the change of it is always non-negative. Okay, and you can prove this non-perturbatively, just for any action. And you can also prove a slightly stronger result, this local version of the second law, that the divergence is non-negative perturbatively in derivative expansion. Okay, perturbatively in derivative expansion. So let me just give you a quick outline how the proof goes. So here you have a Z2 symmetry, and so this is a Lagrangian density. And so this Lagrangian density under the, so tilde again denotes the transformation of this Z2. So under this Z2 transformation, the action is invariant. Yeah, but the Lagrangian can differ by a total derivative. Okay? And then this is rather similar, say, to the standard Losser procedure. And now as in the Losser procedure, you impose the equation motion on the left-hand side. Okay, you impose equation motion on the left-hand side. And in the standard infinitesimal continuous symmetry, in the Losser case, then the left-hand side becomes a total derivative, and then you get a conserved current. But in this case, because this is only a Z2 symmetry, so this is a finite transformation, and when you take equation motion, the right-hand side actually does not go to a total derivative. But nevertheless, you can write the, after imposing equation motion, you can write this equation in the form of the total derivative of some current, but the right-hand side is now no longer zero. Okay, it's some complicated thing which depends on your action. But now you can just apply this Z2 over and over, this Z2 symmetry and over, and then you find that this right-hand side actually can be written in terms of an integral transform of the imaginary part of the effective action. Okay, and in particular, this integral transform actually maintains the non-negative properties of this imaginary part. Remember, one of the unitarity constraints is the imaginary part should be greater than zero. And this actually, this integral form actually maintains that kind of positivity, and then you deduce, and from there, then you can actually deduce these two things. Okay. Also now you find in the equilibrium limit, the current you derived this way just recovers the standard expression for the thermodynamic entropy. And also in particular in the ideal fluid limit. So in the ideal fluid limit, which there's, in action there's no derivative. Okay, if you can see apply this to ideal fluid action. And in the ideal fluid action there's no derivative, and then actually this reversal in the spatial direction then is no longer important. Okay, it does not play any role. And then you can forget about the reversal in the space-time. And then if you forgot about this reversal in space-time, so this is actually essentially become a continuous transformation. So this essentially enhances into a U1 symmetry, and then you actually have a conserved current. Okay, and so this is consistent with that in the ideal fluid limit, of course, the entropy should be conserved. Okay, and I should mention that this U1 symmetry without this minus sign is essentially this U1T symmetry introduced by Hale Logarithm and Ragammani, which their original motivation was precisely try to derive the entropy from some kind of lossal procedure. Okay. Okay, so finally, let me just mention a little bit where does the arrow of time come from. So, so here we have this D2 transformation. So it turns out that the key is that the D2 transformation, this plus sign is not essential. Okay, you can actually also change it to a minus sign, and essentially nothing changes. Everything works. Everything works. Say the first law works, and the fluctuation dissipation works, and the on-target relation works. But the only thing changes is that when you change the plus to minus sign, is actually the divergence of entropy current actually changes sign. Okay, and then you actually find that now the entropy current is monotonically decreasing. Okay, monotonically decreasing. And you find that the causal arrow of time is also reversed. Yes, I should mention that in this system there's also causal arrow of time. Because this is a dissipative system, and when you, the friction, for example, should be positive rather than negative. Okay, and when you do a perturbation, the response should come after the perturbation rather than before the perturbation. And so there's also causal arrow of time, and you can show that the causal arrow of time always coincides with this thermodynamic arrow of time. Okay, and when you reverse this, the causal arrow of time also reversed. And so you can ask, what's the sign? What does this sign really correspond to? So it turns out that this sign corresponding to the following: the plus sign corresponding to you prepare your state at the minus infinity. Say this is your initial state. Okay? And the minus sign corresponding to this state is prepared at t equal to plus infinity. And then this makes perfect sense, because in order to, and when you have a minus sign, which you have to prepare this state at plus infinity, that means your time evolution have to be precisely fine-tuned, so that at t equal to plus infinity, and you precisely go to this state, okay? And that will lead to the entropy decrease. Yeah. And actually, this situation is exactly the same as in the Boltzmann's H theorem. And again, there, in the Boltzmann H theorem, there's also a subtle choice of boundary condition in time, and which leads to this. Okay, yeah, but entropy actually always increases, evolving away from the state. So if you choose the time to go to this direction, and then still increases. Okay, so let me just quickly emphasize the features. And here, the thermodynamic entropy is emergent, and the consequence of some D2 symmetry. And so this is in contrast with the Boltzmann H theorem, who started with a cross-grained, say, this trace rho log rho. And also the monotonicity actually comes from the classical element of the quantum unitarity. And the arrow of time comes from the boundary condition in time, and this is the same, say, as in the H theorem. And so, so it's interesting that the system actually needs to have underlying discrete symmetry involving time reversal, okay, in order to prove this. Yeah, so now let me quickly mention some future questions. So the first, even though here the entropy is an emergent concept only from this D2 symmetry, but there must be some kind of quantum information origin of it, okay? So at the purely mathematical level, say we find that this partial mu S mu equal to integral transform of the imaginary part of the effective action. Actually, at the mathematical level, this integral transform resembles very much the relation between the modular operator and between the integral transform between a modular operator, between the variation of a modular operator and the density matrix, okay, and the density matrix, and so this so this suggests there must be some kind of quantum information origin of it, and if we do find it, and then this would be very nice, because that will provide some kind of effective field theory point of view to think about maybe quantum informational questions, okay. And also, of course, it would be interesting to include the classical and the quantum fluctuations. And here you might see the generalizations of this kind of Jasinski or Crookes relation. And also it would be interesting to understand the Z2 part of this gravity, may give you a hint how to formulate the black hole, and finally, maybe, whether it's possible to relax this Z2 symmetry to actually include more general non-equilibrium states. Yes, I will stop here. Thank you.
Questions?
I mean, there are systems that do not have time reversal symmetry, but they still have a second law.
Yeah. So that's but the one intriguing thing is that essentially all existence proof of the second law, they all require some kind of time reversal. And for example, in the original formulation of this H theorem, the time reversal played an important role. And also, there's another way one can also deduce the second law indirectly from this Jarzynski and Crookes kind of work relation. And there, the time reversal also plays a crucial role. Yeah, so it's a little bit mysterious, I don't know. Somehow time reversal, at least some operation involving time reversal seems to be very important.
Two questions, please. First, this KMS kind of relationship that the relationship that you put involving a temperature was motivated by thermal equilibrium. Now, hydrodynamics, order by order, and the derivative expansion moves away from thermal equilibrium. So you might have expected that this relationship could be modified order by order in the derivative expansion. Could that happen? Could that give you something more general?
Yeah, that's certainly a logical possibility. Here, we actually, the KMS, so here there's a very non-trivial step here. So you actually, because here, so the KMS relation is a relation on the correlation functions in the thermal equilibrium. So we just take that as inspiration to guess something which somehow should work more general non-equilibrium states, say maybe in the local equilibrium. And so certainly logically, something like you said can happen. And so what we found is that this kind of transformation, which you have to really guess how they act on the dynamical variable, they seem to work. Yeah.
Okay. Second question, please. If you applied your setup to n equals 4 Yang mills, there's some parameter that justifies making the whole procedure classical. There's a parameter that would justify doing classical physics rather than doing a path integral of your effective action. I want to know, is that parameter n square, or does it work at arbitrarily strong coupling, but just as long as n square is large, or more?
Right. Yeah. So you're asking whether for the n equals for super Yang mills, you can take the classical limit. Is that what you're asking?
Yeah, I'm saying that to use classical equations of your action, is it sufficient that n square is large for arbitrary lambda? In the case of
yeah. So for the equation motion, that essentially is the thermodynamic limit. And so the dynamic limit is essentially, say, an equal to infinity limit. So and essentially all this, you want to take a number that goes freedom go to infinity.
So everything you've done would apply as long as n is large, no matter how large lambda was, just to confirm.
I didn't hear the second.
Sorry, everything you've
last
done,
sentence.
Everything you've done would apply if n was large, no matter how, even if lambda was very large, right? Just to confirm.
Even the lambda is small, you say?
Even if it's large.
Even the lambda is large. Yeah, that's right.
Okay.
Yeah, you want the lambda to be large. Yeah.
Okay, one last. Sorry. It was my understanding that 3-4 years ago, Shayantani Bhattacharya proved a theorem that sounds very similar to what you said.
Okay.
She proved that in any system that admits equilibrium, that equilibrates, and has positive viscosity and conductivity, it admits a local, an entropy current that has a positive divergence. The assumptions seem very similar because the viscosity being positive can be proved from unitarity. So I was just wondering whether there was a relationship between your two.
Right. So as far as I understand, her proof was just started from, her construction was started from the hydrodynamics. And to show from hydrodynamics, you can always, order by order, construct entropy current with non-negative divergence. So here the starting point is completely different. So here you really look at a general effective action, and you just impose some symmetry, and then you see what comes out of it. Yeah, we are not starting with hydrodynamics, and we're not doing order by order construction of anything. Yeah.
One.
Let me follow up on Shiraz's question. So if you have, let's say, SU2 super young males at G equal to 1, okay, does this discussion apply? I would expect it to apply at very long distances. Is it true or not?
Yeah, so for example, you don't have to do SU2, you can do U1. So let's just say do QED. Say if you do a photon gas, and then we need to take the volume go to infinity limit. Again, the thermodynamic limit would be the volume go to infinity limit.
Okay, I think we need to close, but I'll end with a comment to answer Shiraz's question that the construction that Hong described is essentially what Shantanu discussed 4 years ago.